welcome Mindsetters to Learn Extra Live. We are doing grade 12 mathematics with Heather. Heather, how are you today?
I'm great, thank you. How are you?
I'm fantastic, thank you.
Good.
Grade 12s, we have an exciting show today with a new surprise as well, Heather. We'll be having a new teacher in later. I know you guys are very excited for nice little surprises, so we'll do that later. Hey, Heather?
Yeah, we'll keep them kind of
We'll keep
bated
them-
breath and then we'll surprise them later.
Yeah,
Cool.
that'll be fantastic. What's up today in the show?
Well, what we're going to be doing is just sketching a cubic curve, and you guys know how important sketching quadratics was last year and straight lines the year before that. So it's one of those things that it's actually very, very important for drawing functions in your grade 12. So I'm hoping that you've got your pens, your paper ready, and your calculators, and
Yeah.
let's go to a break and then we can come back.
Then we can do that, guys. Before, actually, you know what? Let's just go straight to it.
Okay.
But before that, let me just remind them of their Facebook page, guys. Remember, facebook.com/LearnExtra and our Twitter handle @LearnExtra. Breaks kind of waste time, and I know you grade 12s love getting right into it. So Heather, over to you.
Okay. All right. So guys, what we're going to be doing is drawing a cubic function. So of course, what is so important is that you understand that a cubic, different to a quadratic, has got this thing in it that has got a power of 3. Okay. So there we go. So remember that if you had something that was a quadratic, we were working with a function that was ax squared plus bx plus c. So that's our quadratic, all right? Here is our cubic. So can you see that you've got a cubed term, you've got a squared term, you've got a plain x term, and then your constant term this time is called d. Okay, what we're going to do is we're going to go through the defining features of it and how to draw it. All right, now what I want you to have a look at is what we have here. Okay, can you see that what I've written is that the graph always has one y-intercept and either 1, 2, or 3 x-intercepts. Now you might be thinking, where on earth does she get that from? And so what I want you to just think about is when we had our quadratic, all right? Think about our quadratic equation, which looked something like this. Can you remember that when we drew a quadratic, it either looked something like that, or it looked something like that, and finally it might have looked something like this. All right. Now, can you see that in each of these cases, here is the one y-cut, here is the one y-cut, and here is the one y-cut. So it seems that there's only one y-cut. But look at the different variations that we can have of how many x cuts. Can you see here we've got 2 x cuts, so that means that when we factorize the quadratic, we got 2 answers. Here, when we actually tried to factorize the quadratic, we got no answers. So this is 2 cuts, all right? This here is no cuts. All right, and you guessed it, this here is 1 cut. Now, what we're going to show you throughout this lesson, okay, this is not getting as much responsive as I wanted, is that when we draw our cubic, can you see that in each of these cases, let's take this top one, can you see there's 1 y cut? All right, here, this one, there's 1 y cut. Here, there's 1 y cut. Here there's 1 y-cut. But in that top graph, can you see there's only 1 x-cut? Here, the yellow graph, there's actually 2 x-cuts. And in the blue graph, there's 3 x-cuts. Okay, so that's what we're going to start remembering, is that only 1 y-cut, and then there's either 3, 2, or 1 x-cuts. All right, so let's get going and let's see what happens when we go to the next slide. Now, I'm sure that your teachers at school have said to you, when you draw a quadratic, there's steps that you have to do. Step 1, find the y-intercept. So how do we obtain the y-intercept? Like in a quadratic, we let our x value be 0. And then we solve for the corresponding y value. Okay, same thing as in a quadratic, so there's not going to be anything nasty there. Then your teacher would have said to you, okay, so now we've got the y cut, we need to find the x cuts. All right, x cuts, x intercepts. How do we do that? Well, we let y be naught, and we solve for the corresponding x values. Okay, now here I've given a little bit of a hint. I've said that we can use one of three methods. Either we can use long division, which is a method that I really don't like, or we can use the remainder factor theorem, which I love, and you'll see me using that, or we can expand and compare coefficients, and I'm going to show you how to do that too. All right, so let's launch into what I mean. Right, so for 8 marks, we need to start drawing this cubic function. So step 1 is we definitely want our y cut. All right, so are you all remembering? For our y cut, we're going to let x be naught. All right, and so what is happening is we're going to work out the function's value at naught. And of course, you can see that that is going to be naught cubed. Take away 6 times naught squared. And 9 times naught, take away 4. Okay, I'm sure all of you are not even going to bother with that step because you can see that the answer is just going to be the constant value at the back there, which is minus 4. All right, so I know, importantly already, that this function crosses the y-axis at a value of minus 4. Okay, nothing difficult there. Now let's have a look at our x cuts. So for our x cuts, and I'm noticing here that our actual screen is showing that 4 in a blue, which doesn't show up that much, so we've just changed that to read x cubed minus 6x squared plus 9x minus 4. All right, so for our x cuts, remember what I said that we have to do? We have to let our y value be 0. Right, so I'm quickly going to say I've got to get x cubed, take away 6x squared, add 9x, subtract 4 is equal to my y value, which is my f of x value, which is 0. Okay, now for those of you who have done a little bit of this theory before, please bear with me, because once you've done it, it's pretty simple, but it does take a little bit of time to get to it. All right, what I say to my pupils is you've got x cubed. Now that must come as a result of 3 brackets perhaps being multiplied by each other. All right, so there would perhaps be an x here, and there would be an x there, and there would be an x there. And can you see that if I multiplied this x by that x by that x, I would get this x cubed? So that's my intention, just like with a quadratic. Remember, with a quadratic, if I had something like x squared minus 5x, let's say plus 6 is naught, we knew that we were going to try and force it into 2 brackets. Here we're just going to try and force it into 3 brackets. Okay. Now remember when you did quadratics, guys, you had a look at this number at the back. That number being a 6 kind of told you what numbers could possibly have been at the back there. All right? I could possibly have had a 1 and a 6, or I could possibly have had used the factors 2 times 3. So that's the logic that I'm going to use here. I look at this back number, all right, and my back number, or my constant number, is actually a 4. Ignore the sign for now. Okay, ignore it for now. Now, how can I get to 4? Well, I know that the factors of 4 are definitely 1, 2, or 4. So I know that somehow these brackets are going to contain 1, 2s, or 4s. Okay? Now what we use is something called the remainder factor theorem. So what we're going to do is we are going to take the function value at 1, the function value at 2, all right, and see what happens. Now, if we take the function value at 1, all right, what we've got is 1 cubed, take away 6 times 1 squared, and 9 times 1, take away 4. All right, now those of you who've got your brains out, that's 1, take away 6, add 9, take away 4. All right, that comes to 0. Now by comparison, let's do the f of 2. The f of 2 would be 2 cubed, which is 8. Take away 6 times 2 squared, which is 6 fours, which is 24. And 9 times 2, which is 18, take away 4. Now, if I add that up, I don't actually care what number it comes to, but it's not a naught. Now, what I'm trying to show you is that because it's not a naught, oopsie, okay, because it's not a naught, that is telling me that the bracket x minus 2 is not a factor. All right? However, because the f of 1 did come to naught, that is telling me that x minus 1 is a factor. Right, can you see that if I put x minus 1 equal to naught and solve that, I get x equal 1 as being one of my answers that made my thing naught. So I now know that x minus 1 is one of my brackets. How cool is that? All right, remember, we've got to try and get 3 brackets. So our one bracket is x minus 1. We've still got a mystery in terms of these 2 brackets. Okay? So this is where it gets just a little bit sneaky, and 2 different methods are possible. All right? What I do is as follows. I say x minus 1, and then I know that what I've got here is my quadratic factor. Okay, hopefully you all understand that what I'm going to need is, because I've got one factor which is linear, I'm going to need another factor which is quadratic. Okay, power 2. Now, let's use another color so that we can be bold. This x multiplied by that number in front has to get me back to my x cubed. So I'm hopefully not shocking you and saying, so that has to be an x squared. Okay? Now can you remember that my back number, all right, if we scroll up, my back number was a minus 4. All right? So that means that when I multiply this chap by that chap, I have to get minus 4 as my answer. All right, so minus 1 times what gives me minus 4? That thing there has to be a plus 4. Okay, so let's see how far we've got. We've got an x minus 1, we've got an x squared, and we have got a plus 4. Now let's just remember what we're comparing it to. We're comparing it to x cubed, right? Minus 6x squared plus 9x minus 4. So minus 6x squared plus 9x minus 4. That's what we've got to get this multiplying out to. So this is the sneaky thing that I do. All right. Can you see that this here, if I multiply the 2 together, all right, gets me to a negative x squared. But can you see here that I've got negative 6x squared. So the only way I can get from negative x squared to negative 6x squared is to actually have another negative 5x squared. And that is going to have to get me to my total of negative 6x squared. Okay, let me repeat. When I multiply those two together, I get negative x squared. Looking at this, I need negative 6x squared. So I'm comparing with what I've got with what I need. Okay? So I've got my negative x squared. I need negative 5x squared more to get to my negative 6x squared. So the only way I can get that negative 5x squared, you've guessed, is as a result of that being multiplied by whatever goes in there, my x term. Right. How am I going to get negative 5x squared? Only if I take x and multiply it by another negative 5x will I get that negative 5x squared. Okay, so I'm hoping that you followed how I have managed to use my linear to get to my quadratic. Right, so we do actually need to just go back a little bit to find some space. Okay, so now I have got it reading x minus 1, x squared, minus 5x. Sorry, that looks disgusting. I wouldn't be able to read that if I were you. Okay, so x squared minus 5x plus 4. And that is what we've now got our cubic transformed into, a linear and a quadratic. Now you're going to say to me, but you wanted 3 brackets, and yes, I did. And can you see here that all you've got is a quadratic that you're quite comfortable with? We know that we can factorize this into x with x. The 4 we can make into 4 times 1. Right, and then we are obviously going to need a minus and a minus equals 0. Right, so what have we got our x cuts to be, or our x answers? The one x answer is going to be 1. The other x answer is going to be 4. And now are you thinking with me, how many x cuts has this particular cubic got? 1, 2. We haven't landed up with 3 unique answers. We've landed up with only 2 answers. So I'm thinking that my graph is only going to cut that x-axis twice. Okay, that's been a lot to comprehend in a short while. So what we're going to do is go for a break. But in the break, I'm going to disguise myself and I'm going to come back as
a brand
new teacher. In fact, I would have transformed gender, right? And I would have actually lost about 20 years. And so we're going to come back just after the break with our new presenter who we welcome this evening. And we'll see you after the break.
Yeah, guys, remember, very exciting stuff happening next. So stay tuned, stick to those seats. See you after the break. Welcome back, Mindsetters. I told you that we'd have a new teacher. This is Iti. Iti, welcome to our Mindset Learn team.
Yes,
Thank you very much for being here. And I know you learners are very excited by our new teacher. And you guys will learn so much. And you guys are welcoming as well. So you'll have a lot of fun with us here at Mindset. Definitely. Do you want to tell us a little bit of what you're going to be doing today?
Katleho, today I will proceed from where Heather left off today. And I will do the turning point as one of the features to proceed with.
Awesome, awesome. Guys, get some pens ready, get your water ready, because it's going to be a fantastic show. See you after the break. Welcome back, guys. I hope you're ready for another fantastic segment of the show, a very exciting one as well. Remember, there are a few things actually to remember. Remember, number one, that we have the giveaways, the Casio calculator and the labeler to the winners. And as you've seen on the page already, there's been winners from last week. You guys know yourselves. So just try send in your emails very quickly so your stuff gets over to you. And winners for this week and next week, remember, guys, all your motivational stuff, your questions, everything you need, every single thing you need. It'll be fantastic to hear from you guys as well. And I'm sure, Mr. Iti, you're also excited to hear from our learners today. So without further ado, over to you.
Thank you, Katlego. Now, I'll proceed from where Heather left it. As she indicated, there are defining features for a cubic function, and we have covered the x and y intercepts. I am now going to do the turning points. What I'll want you to recall is that you learned about the derivative of a function, and a derivative of a function at a given point is actually the slope of a tangent at that curve. All right, if I draw a curve, like that. In fact, let me use the graph that I have on the left, on the right-hand side of this board. What you will see there is that I have represented a few tangents, typical tangents being the inclined tangents and the horizontal tangents to the curve. What you will notice on this graph is that for the horizontal lines or horizontal tangents, your derivative, your first derivative is actually equal to 0. And that you find with the top turning point and the bottom turning point. The slope is equal to 0 for those tangents. Now, if I can just erase this and just proceed from there, all right, at the back. Oh yeah. All right, a few things to learn here about these pens. So we're going to proceed and say we had a function that said f of x. Okay, take a pen from there, right? Choose a color, I think it's still fine. There, get, yeah, this one. All right, so let me choose this one. So if I have f of x, and this is how we represent the first derivative. So the first derivative for this given function is going to be 3x squared minus 12x plus 9. The constant term falls away because it had x to the exponent 0. So like I said earlier on, the first derivative is equal to 0 where you have horizontal slopes, horizontal lines as the tangent. So we equate that to 0, and voila, all we have is a quadratic, and we can actually factorize that and find the values corresponding to those turning points. There, if I take out 3, I will have x squared, take away 4x plus 3 equal to 0. The 3 falls away. There's no way 3 can come back and be equal to 0. All right. So if I factorize this, I'll have x. I'll have 2 factors, obviously. I'll have x minus 1 and x. All right. So I'm going to extend this page so you can see some more of this here. So this is how it factorizes. And what do you have? You have that x minus 1 is equal to 0, or x minus 3 is equal to 0, from which you obtain x equal to 1, or you obtain x equal to 3. That's not the end of it, because we are looking for the turning point. We need the y coordinate as well. Okay, if I can just move this board further down. All right. So to find the y values, we are simply going to into our function. Here is where many people get it wrong. They go and substitute into the derivative function, and that is a gross mistake. So you have to substitute back into your function of x. So we'll say function of x at x equal to 1 equals to, and when we go back to the function, quickly, all right. So if we go back to the function and we substitute where we see x, we put 1. I'll remember that. So that is 1 to the exponent 3 minus 6 into 1 to the exponent 2 plus 9 times 1 minus 4. So what do we get? We get that f of x, which is actually your y value. Look at it. It comes out to be, that's minus 10 plus 10. So that comes out to be 0. So now we have a value of y, that corresponds to our value of x equal to 1. We need to go further and find the other turning point. So, okay. Right, we substitute the other value of x into the function of x, and what do we get? We get 3 cubed minus 6 into 3 squared plus 9 times 3 minus 4. Quickly, that gives us 27 minus, that should be 54 plus 27 minus 4. You can see that 27 and 27 gives you 54. Then this part falls away. You are left with y. The corresponding y value becomes y equals to minus 4. We now have our two turning points. If we combine that with the information that we got earlier, we are in a position to plot all those values and then connect them up. Okay, just extend it further. All right, so we said, what do we have? We've got our turning points as, what was it? That was 1 and 0, and the other one was 3 and minus 4. And let's just recall the information that we obtained earlier, which was the x-intercepts. I think it was our x-intercept were 1 and the other one was 4. Okay, and our y-intercept was minus 4. We are in a position to mark all these points on the graph, on a system of axes. Okay. All right. So we said we've got 1, and we've got a 4, we've got a minus 4. I hope I remember all of this. Minus 4, and we had for the turning point a 3 corresponding with a 4 there. The other turning point was 1 and 0. So that was our x-intercept, the two x-intercepts, our y-intercept. Now, how do we tell which way our graph is going to face? First of all, you've got two turning points. One has got a bend that is facing down, and the other has got a bend that is facing up. Now, the fact that your equation, what we had was x cubed minus 6x squared, all that, the value of a in front of that x cubed is positive, tells you that your graph is going to start with a positive slope and end with a positive slope. if that value of A was negative, your graph was going to start with a negative slope and end up with a negative slope. In between is the opposite slope. In this case, we know that this is the turning point, and that is the turning point. And this graph goes like that. Another thing that you may be asked is the point of inflection. The point of inflection, interestingly, is basically the midpoint of these two turning points. Right in the middle of that, which is at x equals to 2. But there is another way of finding that. You could actually find the second derivative of the function that you started off with. Okay, if I may just go up here to remind myself what I had. That was the derivative was 3x squared minus 12x plus 9. Quickly, so 3x squared minus 12x plus 9. Okay, let me just get a bit of an eraser there. Okay. All right, so now I can write 12 there. Oh, good. So, what we said is this was the first derivative. Now we are looking for the second derivative. Where the second derivative equals to 0, it corresponds to that midpoint of the two turning points. Second derivative, we represent it with 2 double dash. That equals to 6x minus 12. If we equate it to 0, we get the x value that corresponds to our point of inflection. X comes out to be equal to 2. And yeah, that basically covers what I wanted to discuss for the rest of, we've covered all the features that needed to be covered about this graph, and probably what you need to show in the end so that you don't lose marks is to show this actual coordinates here, although you have marked them like that. So this one as well, it's 1 and 0. So you've got everything you need, and probably you need to show that this is the y-axis and that's the x-axis. All right. So basically, Katleho, this is what I wanted to discuss,
I think some learners have some questions, so would you mind answering some?
Yes.
Letitia asked, what is concavity, local max, and local minimum, if this is related to what you're doing?
Oh, exactly. Now, this terminology, I didn't want to dish it out, because I wasn't sure whether some people know it or not.
Okay.
But when you talk about concave up or concave down, you're talking about these two bends of our graph. When it faces down, we say it's concave down. Yes. When it faces up, we say it's concave up.
Oh, okay.
Okay. And if you can allow me to use that terminology about the point of inflection, where your concavity changes from facing up to facing down corresponds to your point of inflection.
Oh, okay.
Okay. Another way of looking at it would be to say, if you had a tangent tracing this curve, it would actually it is actually rotating in the clockwise direction, and where it starts turning to go anti-clockwise, that is also the point of inflection.
Oh, okay.
You can imagine if your rotation, you define it as positive for clockwise and negative for anti-clockwise. In the middle of that, there must be a 0.
Oh, okay.
Okay.
Okay. So are you ready to go for a little break?
Yes.
Okay, guys, we'll be going for a little break. Remember, when we come back, all your questions answered. Send in all your questions, all your queries on this graph and what Heather did before the other break. So make sure that all your questions are ready and sent through so that we can target that as soon as we get back. See you after the break. Bye. Welcome back, guys. I know you guys had a fantastic last session with E.T. He was very excited to be with you guys, and you guys did mention that he was awesome. I also think that he was awesome on our live show, and thank you guys for your warm welcomes. Also, here at Mindset, we have some magic tricks. We're very good at them, so our teachers always transform. And you'll see just now what transformations that we have up. Remember that, guys, we have the Casio calculator to give away, as well as the labeler. So keep sending in all your questions and everything. This is what we're here for. We're here to answer your every question. And I know grade 12s are very keen on learning. So here we are. Over to you, Heather.
Okay, so here I am, back in the flesh again, aged a bit, put on a couple of kilos, but yes, it's me. Okay, so guys, what I really just want to do is emphasize a couple of things that come up in our papers at the end of the year that both E.T. and I have not covered yet. And the one thing is that somebody asked, what is a local minimum and what is a local maximum? Now, you must remember that if you are drawing a parabola, all right, this is what we would call a minimum turning point, because that is the all-time low that it'll ever get to. So in other words, if we were talking about the range of this particular graph, let's just say that this had coordinates 2, -3. All right, our range would be y going from -3 up to infinity. Okay, so it is the minimum. It will never go lower than -3. But unfortunately, in our cubic, all right, this is a turning point for sure, but we would call it a local max turning point, and here we would call this one a local min. Now, the only way, or the only reason that we have that terminology is, can you see that in this area, this is the maximum that the graph reaches. But over here, very definitely, it goes a whole lot higher. All right, in this location, it goes down to -4. But for certain down here, it goes lower. So in fact, our range is going to be from negative infinity all the way up to positive infinity. But in this area, this is the minimum that it goes to, so that's why it's called a local min. And in this area, just in this little bit of discussion, that's a local max. Okay, so that's answering the previous question. The next thing that I just want to discuss very quickly that teachers love to put in papers is, when is the graph increasing? All right? And when is the graph actually a decreasing function? All right, now looking at your graph, can you remember what E.T. said? He said that because our leading coefficient was x cubed, it was a 1. It started off with a positive gradient, then it went to a negative gradient, then it went to a positive gradient. So increasing is actually when is your gradient positive. Decreasing is very definitely when is your gradient negative. Now we actually have 3 things happening on this graph, all right? So this is when my graph is increasing. As my x is getting bigger, my y value is getting higher. So my graph is increasing all this way and moving at the same place, all right? All right, so it's increasing. Then it hits the turning point. Now, the turning point is actually called a stationary point. Okay, now if you are in a car and you are stationary, it means that you are not going forward or back. In other words, your speed is not getting more or less. So at this particular place, all right, you aren't increasing or decreasing, so that is called stationary. All right? Now, this portion of the graph is where you are decreasing, because you can see that this y value going compared to that y value, your y values are getting less. So those are decreasing. Then all of a sudden, you start increasing again. So this graph, you've got a portion that increases, then it becomes stationary, then it decreases, then it becomes stationary, and then it increases again. Okay, now I know that one of the problems that a lot of people have is, okay, so you've explained to me what happens with a positive x cubed, but now what happens with a negative x cubed? And you can see there that E.T. is a fantastic presenter because he presented and prepared the slide. You can see that what you've got, when your A is positive, it starts off being positive, then it changes to decreasing, then it goes back to increasing again. However, if you have a negative, all right, so let's just say we take a negative x cubed plus some number times x squared plus some number times x plus a constant. Because this value here, guys, is negative, all right, you have to imagine that what is happening is that you are putting in a very negative value, all right? And so this is negative. Now, what did E.T. say? That if your corresponding coefficient of x cubed is negative, all right, your slope has to start negative, in other words, decrease, then it has to increase, and then it has to decrease again. So your graph is going to look something like that. Some people, not me, some people call this a slinky curve. Not such a nice color to use. Some people call this a slinky, and some people call this a kinky. All right, I don't like those things, but you know, whatever gets you, if that's how you remember it, that's absolutely fine. All right, the next thing that we need to just have a look at is going backwards. Now, you know that in grade 9, they taught you how to draw the straight line graph. Then they gave you the picture and made you find the equation. Then, same thing with the quadratic last year. Now, the other thing that they need to test is if they give you the graph, can you actually work backwards to find the equation? All right, this is actually quite easy, so it's not going to take me a long time. So let's focus on this picture. All right? Can you see at the moment that I've got some very important information? I've got that the 1x cut, I don't know if you can see, it's a little bit small, but I've got my 1x cut is at -7. All right. Then I've got another x cut at 1, and I've got a third x cut at 6. So you are actually in a position now to say to me that my function, all right, cut at -7, which definitely means that the 1 bracket would have to have been x minus 7 when we factorized it. All right? That is a 1. So tell me if you understand then that the other linear factor would have to have been x, and that's my mistake, not x plus 1. Can you see what the mistake is that I made? All right, it's not a plus 1. If I want a 1 as an answer, what is this going to have to be? X minus 1. Because I need 1 to come out as the x cut. Lastly, 6, you can see that that is going to be x minus 6. But now I've got a problem. Because there are other graphs that also go through -7, 1, and 6. So I hope that you can see, if, for example, I had done that graph, that also has cuts -7, 1, and 6. So when I find the equation of any cubic, I must make sure that I introduce a value of A. Now, what we have on the board is not enough information. Because I have used my -7, I have used my 1. Let's move that out the way completely, all right? And I have used my 6. I would need to know another point on the graph. in order to find out the value of A. So at this particular moment, I'm going to tell you that that value there is a 2. Let's just say. All right? It looks like it's cutting up at some kind of a positive y value. Now what I would do is I would substitute in that point, and the point is 0, 2, and I would substitute it in to find out the value of A. Before I do that, I'm sending a challenge out to you. When I find the value of A, is it going to be a positive or is it going to be a negative? Okay, no sitting on the fence now, okay? Make up your mind. Is the A value going to be positive or is the A value going to be negative? Have we got anybody screaming answers quickly?
I think that we must give them a few minutes for the answers to stream in.
All right. Guys, can you see what's happening with this yellow graph? It's starting off positive or increasing, then it's becoming decreasing, then it's becoming increasing, which is telling me that my A value is definitely a positive value. So let's just substitute in and see what we get. And I'm almost certain that the numbers I've chosen are not going to be nice, but we're getting the value of 0, 2. So I'm going to have to get 2 is equal to A times -7 times -1 times -6. And yeah, the numbers haven't worked out great, but that's maths for you. So you're getting 2 is equal to -7 times -6 times -1 is going to be a negative 7 6s are 42. All right, and a negative 42A. So in this case, I have got a problem coming up, haven't I? Let's just see. Notice that there. My x cut is at -7, so my bracket had to be a positive 7. Heather, you chop. Right, so that's actually going to be a positive 42A. So we're going to get that A is the value of 1/21. Not nice, but there you go.
Heather,
Okay.
we have some answers if you're looking for them.
I beg your pardon?
We have some answers to your
Super
negative
duper.
positive.
Give me an answer.
Turvin and Kashifa say positive.
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 So they were right
They
all
were
along.
right.
Okay. All right. So guys, what I also just want to have a look at very, very quickly is the most simple cubic. Okay, what if I just gave you f of x equals x cubed? Okay, now this thing, you're screaming it's positive, yes, but let's look at the y cut. All right, do you agree that if I let x be 0, y is going to be 0? That's nothing amazing. Let's look at our x cut. So if I put x cubed equals 0, well, you can see that x is 0, and there's only one answer. So we get a big fat lot of information that our x cut is there and our y cut is there. So that's not too much information as far as I can see. Then remember, E.T. said as soon as we've done that, we now need to find our turning points. So if we take our first derivative, our derivative is going to be 3x squared. And of course, for our turning points, we put that equal to 0. And again, if we divide both sides by 3, that has no effect. But again, x is 0. And so we get our turning point also to be there. All right, so no matter how much work we do, all we're getting is the singular point of interest. So you have to go back to basics, unfortunately. And when you go back to basics, what I mean by that is you are going to have to take a table. So if we take a table, all right, remember if x is 1, x cubed will be 1. If x is 2, x cubed will be 8. If x is 3, x cubed will be 27. If x is minus 1, x cubed will be minus 1. if x is minus 2, x cubed will be minus 8. And I think we've got enough to see what's happening here. 1 and 1 is somewhere there. 2 and 8, all right, is somewhere there. 3 and 27 is somewhere up there off the screen. Minus 1 and 1 is somewhere there. Minus 2 and minus 8 is somewhere there. And so the only way that you can actually plot this is point by point plot. And what you get here is a graph that looks like that. Now, it almost looks a bit like a tan graph, doesn't it? But you go home, you plot more points, and you see that this graph is always increasing. Okay? Never decreasing, always increasing. And this is the graph of y is equal to x cubed. Right, we've done our time.
We've done our time.
Great. And next week, we're going to be doing applications of calculus.
Oh, awesome. You guys
Okay?
heard that. Application of calculus. Yo, what a large word. Guys, I know you guys had an awesome show. Thank you to E.T. and Heather for a fantastic show. Another thank you to Liberty. You guys rock. That's why we're here. Guys, remember, next week, what Heather said we're doing. Matrix, thank you. You've had a very inspiring show, and you've inspired me as well. See you next week, guys. Have a fantastic show. Not have a fantastic show. Have a fantastic after show. Learn more, learn extra. Bye.